Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, one of the things that you hear constantly from the science denial community is you have to do your own research, which is rather ironic because they never do their own research. And when they try and do something that could be considered research, they generally don't have any idea what they're looking at. So I thought today I would go ahead and do something of my own research. And that was, I wanted to personally verify the altitude and the speed of the International Space Station. I used a $30 software-defined radio dongle, which I plugged into my computer, attached it to an antenna, and read the signal from the repeater on the International Space Station, which is on 437.8 megahertz. It's something that any of us can pick up. And using that, I not only verified the altitude of the International Space Station, I was able to measure its speed as well. So let's cue up the music, and I'll show you how I did it and how you can do it as well if you want to do your own research. Eat your heart out, Nathan. Now here's my setup to do this measurement. Now this is my studio/radio room, and right here you'll see the antenna that's on a pole outside my garage, and that's what's called a discone end, and that's a classic omnidirectional antenna used by ham radio operators. Here's my computer. Right here is the software-defined radio dongle plugged into my computer. And down here is where I'm recording everything. So I've got the software-defined radio in the background, and I have the position information on the ISS down here. Let's go ahead and have a look at that. Now here's the readout from the computer that combines all of the displays. Now in the left lower corner, you'll see the position information on the ISS. You'll see the map with the track of the orbit. And then just above it, you'll see a Google Earth image with a crosshair exactly where the ISS is. Now you'll notice that in the background, you'll see my software-defined radio is tuned to 437.8 megahertz. That is the frequency of the radio repeater that's on the ISS. So what happens is somebody sends a message to the ISS, an amateur radio operator. The ISS receives it and rebroadcasts it on 437.8. Now, let me go ahead and minimize myself, and I'm going to let you have a look at this display, and I'll explain to you what you're looking at. All right, so here's the International Space Station, and here it is on the map. Now, currently, this is in the Gulf of Cortez, and that's its location. This is the tip of Baja California, and this is the mainland coast of Mexico over here. Now, what we're looking for is some signals from the ISS to appear on what they call the waterfall display over here. This is moving downward, and when a signal appears, it'll come in as a bright green flash up here, and then it'll just work its way down the screen. So let's go ahead and have a look and see what we can find. So as we come along, as you see, the ISS is moving along. It's coming up over the Rocky Mountains right now, and it's coming into Arizona and Nevada. We should start seeing the ISS signal shortly. Now, as we come through, there's the first signal right there. Now, I don't know if you can see it, but there's a couple of streaks right here. Let's back it up a little bit and you can see it come in. Notice right here that there's a spike, and then underneath it, you see this light green color. So what we do is as soon as we see that, we go ahead and get the frequency and we mark the location by latitude and longitude right down here. So this is called acquisition of signal, AOS, and I'm going to record this information right here. Now what I've done is I've recorded acquisition of signal at 22, 30, and 43 seconds. And here is the actual location for acquisition of signal, 33.83 degrees north, 99.73 degrees west. Now, one thing that you need to understand about radio propagation and electromagnetic radiation in general is that as it comes through the Earth's atmosphere, it does refract a little bit. Now, all things being equal, the refraction has to do with the wavelength of the radiation coming through. So visible light is on the order of 5 to 600 nanometers in wavelength. It's very, very tiny. A nanometer is 1/1000th of a meter. The radio signal coming from the International Space Station on 437.8 megahertz is in what's called the 70 centimeter band, which means the wavelength is some 70 centimeters long. It is many millions of times longer than visible light. Now, as a result of that, visible light is refracted considerably more than radio waves would be. There is, in fact, so little refraction on radio waves that in this particular case, we're going to ignore any refraction whatsoever and treat them as simply being straight line of sight waves. Now, before we move on, we also have to look at one more thing, and that is, what is the frequency of the radio waves that we are receiving? Now, recall that the ISS is broadcasting on 437.8 megahertz. However, when you have an object that is moving towards you or away from you, you get something called Doppler shifting. Now, this is the phenomena you hear when there is an ambulance siren going by or a race car. As the race car is approaching you, it has a very high-pitched whine to it. As it passes you, the pitch begins to decrease. And the reason for that is rather simple. So for those of you that are unfamiliar with the cause of the Doppler effect, let me go ahead and show you real quick. So here we are right here. We're the observer. And here is the race car. Sound waves are being generated by the race car. And as the race car moves in this direction, the wavelength of those sound waves is being compressed. As a result, if the wavelength goes down, that means the frequency goes up. Now, on the back side of the race car, the wavelengths are being stretched out somewhere. So as the wavelength goes up, the frequency goes down. The exact same thing occurs with radio waves. So as the ISS approaches us and closes that distance, what happens is we get the compression of the radio waves coming towards us, and as a result, the frequency goes up. As it passes us, we see the frequency of the waves is the same as the frequency that is being transmitted by the ISS. And as the ISS moves away from us, the frequency that we hear on our radio is lower than the broadcast frequency of the ISS because those wavelengths are being stretched out. And that's the phenomena we're seeing here. The frequency that the ISS is broadcasting on is 437.8. But when we acquire the signal as the ISS is coming to us, it's arriving at 437.81. It's higher than the broadcast, and that is the Doppler effect. Now, as the ISS gets closer and closer to us, the signal gets stronger, but more importantly, the frequency begins to shift. So let's watch. So there is a nice strong signal from the ISS. Notice that there's not only do we have the green here on the waterfall, we see the peak of the signal up here in the frequency. Now, if you have sharp eyes, you'll see that that's starting to move closer to 437.8, which is right here. You see how this is kind of arching over? And here's the location of the ISS. It's in southwest Michigan right now. Now, as we continue on, we get to this point right here. And this is its closest approach to my location. I live up in this area. So the frequency is a little higher here as it's approaching me. it hits the carrier frequency when it's passing my station. And then as it begins to go away, you'll see that it starts to drop and it moves further and further left. Now we continue to watch them. This is what's called the Doppler shift. Now we continue to get out here into Canada and the frequency is getting lower and lower. And then pretty soon, we have no more radio reception. So right here, we're getting loss of signal right about there. So let's go ahead and write down this position. We've got 50.74 degrees north, 58.38 degrees west, and here is the time. So now we have our data. Let's go over it. We acquired signal at 23:30 and 43 seconds at this location, and this is about 1,800 kilometers from my location. Now we lost, and then 4 minutes later, we had station passage. And then we lost signal 5 minutes after that, and that is 2,200 kilometers. So why did we hear it further going past us than coming towards us? Well, there's a couple of possibilities that we're dealing with. First of all, I could have missed the initial signal. Now, there were some very faint signals before I called it as acquisition of signal. Those may have been the initial signals. Recall that in order for me to read a signal from the ISS, somebody has to fire a radio signal at it, and then it repeats it back. It just may have been quiet as it was coming over Baja California. Maybe nobody triggered the beacon. The other thing is UHF radio frequencies, which is what we're dealing with here, are blocked by vegetation. I have trees and I have buildings and church steeples around my house. The signal may have simply been blocked in that southwest direction, whereas I had more of a clear shot going out to the northeast, or the east actually. We're going to use the longer of the two. We're going to use this 2,200 kilometer number because there's no reason that I would hear it 2,200 kilometers in this direction, but only 1,800 in that direction, other than operator error or environmental factors. So the first thing that we're going to do is we're going to figure out the altitude of the ISS using this data. The bottom line is we have line of sight to the ISS for 2,200 kilometers. How high would the ISS have to be in order for us to see it 2,200 kilometers away? Let's go over to Walter Bislin's Advanced Earth Curve Calculator and see if we could figure that out. Okay, so here's Walter Bislin's Advanced Earth Curve Calculator. We've got a couple of setup things to do on here, and we need to approach it from a special way. First of all, we already talked about refraction. Now, with radio beams in the UHF frequency range, which includes 437.8, you're not going to have any refraction compared to looking at light, for example. Now, the other way that we have to have a look at this is, okay, what do we put in for the heights? Now, my elevation above sea level is about 250 meters. We're going to try and find the elevation of the ISS, and the way that we're going to do that is we're going to find the elevation that gives us a horizon 2,200 kilometers away. And the best way to do that is look at it from the standpoint of the ISS. So we don't know the height. We're going to try and put in some numbers to that height for the ISS. That'll be the observation height. And we want to get a horizon 2,200 kilometers away. So let me show you how we're going to do that. Now, first of all, let's go ahead and put in my elevation above sea level, and that is 250 meters. Now, we're going to put the target distance at 2,200,000 meters. Because, Nathan, the way you find the number of meters in kilometers is you multiply kilometers by 1,000. Just trying to help out. Now, if we look down here at the horizon data, we want to see the distance on the surface. And from a height of 2 meters, the distance on the surface is only going to be 5 kilometers. So we need to make this number quite a bit larger. So we're going to start off with 100,000. Now the reason that we're using 100,000 meters is that that's 100 kilometers, and that's the legal definition of the Kármán line, or the edge of space. So anything below 100 kilometers is in Earth's atmosphere. Anything above 100 kilometers is in space. Let's see if we could see the ISS at 2,200 kilometers if it was in the Earth's atmosphere. And as you can see quite clearly, we have over 92 kilometers of hidden height, and the ISS would not be visible. So we're going to have to go higher. Let's go up to 300,000 meters, or 300 kilometers. Once again, if you look right down here, the ISS is still hidden from us by 6 kilometers, but we're getting close. Let's go a little higher. Let's go up to 400 kilometers. See what we have here. So if the ISS was 400 kilometers above the surface, it could see me at 2,200 kilometers. Probably just a little bit less. Let's try 390, just to be honest here. Keep everybody honest. At 380 kilometers, we're about 35 meters visible, and the distance to the horizon on the surface below the ISS will be 2147.8 kilometers. So according to this, the ISS must be between 380 and 390 kilometers above the surface. That meshes pretty well with the data that we are given from NASA. Okay, so we verified the altitude of the ISS, and we verified the fact that it's well above the Kármán line, almost 4 times the distance from the surface to the Kármán line. Now, let's go ahead and have a look at the speed. Now, there are 2 ways that we can look at the speed. The first is rather obvious. 5 minutes is 300 seconds, and in reality, it's about 316 seconds. So we can take 2,200 divided by 316. That gives us a speed of about 6.96 kilometers per second. Just doing a rough estimate, we get 6.96 kilometers per second, simply based on time and distance. But we can do better than that. We can use the Doppler shift to give us a speed as well. So let's go ahead and see how we do that. So we'll go down to the desk and we'll have a look and see if we can math this out a little bit. Now, the formula for the Doppler shift is that the frequency of the sending station over the frequency of the receiving station equals the speed of light versus the velocity of the receiving station over the speed of light and the velocity of the sending station. Now, this is either a plus or a minus. How do we decide what it's going to be? Well, the speed of light is a constant. It's 300,000 kilometers per second. We could use scientific notation for that, but let's just use the regular number. The frequency of the receiving station is related to this part of the term right here. Now, in order to understand the Doppler effect, we have to look at something. And that is that how are we going to approach looking at this problem? Well, we can be an independent observer at 0 speed out here. Okay? And we can look at me on the Earth, and I have a rotational speed. And then we can look at the ISS, and it has a much larger orbital speed. And we can compare the difference between the two. That's a perfectly legitimate way of looking at it. The other way is that we can look at it from the standpoint of the ISS. So we're going to consider the 0 point to be the ISS itself. And the Earth is rotating underneath it, but it's not moving. So we can look at my velocity compared to the ISS. But the way that I'm going to do it, I think, just makes good sense, and that is that I'm sitting here in my studio, and my velocity is going to be 0, and the ISS is coming overhead, and it's going to have a velocity coming over my head. So this is the way that I will look at it, but I can look at it any of these other ways as well. So the ISS is approaching me, and the frequency that I receive based on the Doppler effect will be higher than the frequency that is being sent. So my rotational speed is 0, so that term drops out completely. And C plus Vs is greater than C alone, so that goes along with the Doppler effect. So here is my formula. The frequency of the ISS over the frequency I'm receiving equals the speed of light, because that's the speed the radio waves travel, plus the speed of the ISS. So let's go ahead and see if we can arrange this in a way, because we know that frequency, we measured that frequency, and C, of course, is a constant. We want to know that number right there. So in order to do that, let's maneuver this around a little bit. So let's take this term, and we're going to move it to that side. So we're going to have C plus Vs equals C times the frequency received over the frequency sent. See how we just moved that over to the other side? Now, one last thing, we want to isolate this. So let's take that and say the velocity of the sending station equals C times frequency received over frequency sent minus the C. And that gives us our answer. So let's go ahead and put some numbers in here. So here we go. Now the fun begins. So we've got 300,000 times the frequency received, and the frequency received was 437.81 megahertz over frequency sent 437.80 megahertz minus 300,000. Let's go ahead and do the math. 300,000 times 437.81 equals, divided by 437.8 equals minus 300,000. That gives us the velocity of the ISS being 6.85 kilometers per second. And when we did it the other way, we got 6.96 kilometers per second. Well, let's go ahead and compare these numbers to the numbers reported by NASA for the ISS. Can we verify what NASA said? Well, first of all, can we verify the course of the ISS? Well, yes, we can. Because as you see right here, here is station passage, which occurred about right there. And that's where NASA said the ISS was at that moment. Second of all, we've got the Doppler shift, and we have the distance over time that the ISS traveled. That's very close to the 7.66 kilometers per second that NASA says the ISS is moving. We got about 7. And finally, we got an altitude for the ISS of 380 to 390 kilometers. According to this, the ISS is at 422 kilometers. So we're about 10% off. Now, the way that I calculated this using the Doppler shift calls for the ISS to pass directly over my head. Now, the ISS actually passed about 90 kilometers south of me. So there are some corrections that need to be made. We underestimated the speed of the ISS using the Doppler method. Remember, the time over distance was rather crude. The Doppler method should give us a much closer number. We got within 10%, but I think we can do better if we take into account the fact that the ISS didn't pass directly overhead, but was some distance away. We'll go over that in our next episode, where we look at doing a little bit more precise Doppler estimate of speed. And I think we're going to get a little closer to the 7.66 kilometers per second that NASA reports. So that's how you do your own research. There are two parts to doing your own research. The first is actually going out and getting data. The second is having the knowledge to understand what the data is showing you and how to get answers from the data, primarily by asking it the right questions and using the right tools and mathematics to give you the answer that you're looking for. So this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. I'll see you again soon, and we'll finish this up on our next episode.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.